In this lesson we're going to look at coordinate geometry, and coordinate geometry is a very big topic, so we're just going to look at the sort of basics so that you can understand things later on in the regular course. The first idea is that we have two axes, a y-axis and an x-axis, and these are perpendicular to one another, and they divide the plane up into four quadrants, and the quadrants are numbered, and this isn't all that important, but it does come up occasionally. The quadrant in the upper right hand corner is quadrant 1. Then it goes in a counterclockwise direction, so quadrant 2 is in the upper left hand corner, quadrant 3 is in the lower left, and quadrant 4 in the lower right. Now, quadrant 1 in the upper right hand corner is where we start, because in a way that's where we spend most of our time, because both the x and the y coordinates are positive. So the x-axis has positive numbers on the right, so 1, 2, 3, negative numbers on the left, -1, -2, -3. And the y-axis has positive numbers above, so we have 1, 2, 3, and negative numbers below, -1, -2, -3. And obviously I've just used a few here. The intersection of the two axes is called the origin, and both the x and the y coordinates are 0 there, and it's often just labeled an O for origin, or you can think of it as a 0. So on this coordinate plane we can locate any specific point using an x and a y coordinate. So for example, if we have our x, y axis and we have a point here, it may or may not have a label if we call it point A, for instance. If we have coordinates, say 3, 2, the coordinates are called an ordered pair, so it matters which one is first, which one is second. So by convention, the first number refers to the x coordinate, and the second number refers to the y coordinate. And you put a comma between them and you put them in brackets, and that makes it very clear that this is an ordered pair and it's referring to a specific point. Now, all that means is that the x-coordinate is 3, so you can actually think of it as directions, how to get to that point starting at the origin. The x-coordinate of 3 means you're moving 3 units to the right, and the y-coordinate of 2 means you're moving 2 units up. Right, left is positive and negative in the x-coordinates, up, down is positive, negative in the y-coordinates. Now, that point, obviously, if we superimposed it on a proper piece of graph paper, you would see it was 3 units to the right, 2 units up. Let's take a look at some uses of the coordinate system. One use is we can determine the distance between 2 points. So we're going to actually derive the distance formula. All you need to know to derive the distance formula is the Pythagorean formula, which we've come across before. So let's draw in our axes, and I'll try to make the points here a little bit more accurate. So let's have one point at 210. So we're going to have the background here is going to be 2 units per line. So 2 across would just simply be moving over 1, and then 1, 2, 3, 4, 5. So we can refer to this point up here as 2, 10. So 2 units to the right of the origin, 10 units above the origin. And then we're going to have another point, 8, 2. So 1, 2, 3, 4, and 2 up. So that's 8, 2. What we really want to know is what's the distance between those 2 points, or the length of that line segment. And we can call the length of that line segment d, or we can think of d as just the distance. Now, it doesn't take too much imagination to realize that you can make a right triangle by drawing a vertical line segment and a horizontal line segment. And now you can think of D as the hypotenuse of this right triangle. So what is the length of that vertical line segment? Well, the point at the top has a y-coordinate of 10. It's 10 units above the origin, or if you want, 10 units above the x-axis, whereas the point on the right is only 2 units above. So we can think of the difference between those, 10 minus 2, as the length of this line segment, one leg of the right triangle. Similarly, we can think of the length of the horizontal leg of that right triangle as the difference between the two x-coordinates. The point on the right is 8 units to the right of the origin, or 8 units to the right of the y-axis, whereas the point in the upper left-hand corner is only 2 units. So 8 minus 2 gives us 6. So now we have a right triangle with legs of 6 and 8, and you probably recognize this by now as a Pythagorean triple, and it's an example of a 3, 4, 5 right triangle. So 3 times 2, 4 times 2, 5 times 2. So we know that D is going to be equal to 10. But if we didn't know that, we could use the Pythagorean theorem. We could say that the square of the hypotenuse is equal to the sum of the squares of the other two sides. And if I didn't already know that it was 6 and 8, I could actually say that the 6 came from taking 8 minus 2, squaring it, and the 8 came from taking 10 minus 2 and squaring it. So the D is simply the square root of this sum, and I'm going to use the sort of more complicated sum that we wrote down, and you'll see why in a second. Now, we know that 6 squared is 36, 8 squared is 64. Add them together, you get 100. So the square root of 100 is 10. So this turns out to be, as expected, 10. But the reason why I did it in this more sort of complicated way is so that we can derive a formula. We can write the distance between any 2 points as the square root of the difference between their x-coordinates. So we can write that as x2 minus x1. And the reason, or the way to interpret x2 with that little subscript is it's the x-coordinate of 0.2, and x1 would be the x-coordinate of 0.1, and we square that difference. And then the difference between the y-coordinates we can write as y2 minus y1, and we square that. Now, you may be looking at the diagram thinking, well, how do I know which one's 0.2? How do I know which one's 0.1? Turns out it doesn't matter. If you assign one of the points as 0.2, the other one becomes 0.1, and then you're just looking at the difference. Now, depending on the way you do it, you might get a positive or a negative, but since we're going to square it in the very next step, it really doesn't matter whether it's positive or negative. For instance, using the example above, 8 minus 2 is 6. If you square 6, you get 36, whereas 2 minus 8 is negative 6. And when you square negative 6, you also get 36. So it really doesn't matter which one is 0.2 and which one is 0.1. And this is the distance formula, and this is very useful for figuring out the distance between any 2 points on the coordinate plane. Now let's take a look at another another property of points on the plane, and that is called slope. So slope is a measure of steepness. So if we have 2 points on the plane and we draw a line between those 2 points, or we have a line segment connecting those 2 points, the question is, how steep is that line segment? So let's say this is the point 3, 2. So it's 3 units to the right, 2 units up. I'm not going to draw the axes just because I want this diagram to be sort of as clutter-free as possible. And let's say we have another point, 8, 5. So it's 5 units to the right. So 1, 2, 3, 4, 5 units to the right. And it's 3 units up. 1, 2, 3. And so there's my point 8, 5. And I've got a line or line segment. So I'm going to do the line. So there's a line passing through it. And once again, it doesn't take too much imagination to think of a right triangle. And we can refer to the legs of the right triangle as the horizontal difference and the vertical difference between the 2 points. Another way to refer to them is the vertical difference between the 2 points is often referred to as the rise, and the horizontal difference between the 2 points as the run. So slope is simply the ratio of the rise to the run. And there's a letter that is traditionally used for slope, which is m. Apparently in different cultures, different letters are used, but in most of Western mathematics we use an m. So the slope can be calculated by calculating the rise. Well, what is the rise? The rise, again, is the difference in the y-coordinates. The y-coordinates tell you how many units above or below the origin you are. So in this case we have y-coordinates of 5 and 2. So we get 5 minus 2, and that's going to equal 3. And the run is the difference between the x-coordinates, so 8 minus 3, and that's going to equal 5. So we have a rise here of 3 and a run of 5. The ratio is 3/5. Now there's another way to interpret that number. That number tells you how many units up or down, if it's a negative number, you are moving on the y-axis if you are moving 1 unit to the right on the x-axis. So in other words, as we move 1 unit to the right from the point 3, 2, we have to go up a certain amount to stay on the line, and the distance we have to go up is this slope, 3/5. If we go to the right 1 more unit, we go up another 3/5, and if we can continue this, we go to the right 1, up 3/5, to the right 1, up 3/5, to the right 1, up 3/5, and eventually we get to the point 8,5. So that's another interpretation for slope. Now this line is going up and the slope is positive. If the line is going down, the slope is going to be negative. So let's take a look at an example of a line with a negative slope. So let's say we have a point up here at 2, 9, and then another point 6 units below it, so 1, 2, 3, 4, 5, 6, and 3 units over, 1, 2, 3. So that's the point 5, 3. So this line is going down as you go from left to right. You should always think of going from left to right, just the same way that you read. If you always think of going from left to right, then you're not going to get confused as to what's up and what's down. So again, if we draw the vertical and horizontal displacements and make this into a right triangle, we can think of the rise and the run. And in this example, when you're looking at a triangle, you always label the sides with positive numbers. And so it's not necessarily that intuitive to think of the vertical as a -6. But if you make it a 6, that's okay too, as long as you keep in mind that because it's going down, it has a negative slope. So when you actually go to calculate the slope, you've got m. If you've got a diagram to work with, I usually start with the point on the right and then subtract the values from the point on the left. So for instance here, for the rise, the change in the y values, I would do 3 minus 9, and then for the change in the x values, I would do 5 minus 2, and that would give me -6/3, which is -2. But it really wouldn't matter if you started with the other point and you said that it was 9 minus 3/2 minus 5, because that's going to change the signs of the numerator and the denominator. You're going to get 6/3, but it's not actually going to change the sign of the ratio. The ratio is still going to be -2. What you must not do, what you have to guard against doing, is starting with one point and subtracting the y values, and then starting with the other point when you subtract the x values. Then you will get the sign wrong. Now if you always just look at the diagram or think of the diagram and know that it's going down, meaning a negative slope, or going up, meaning a positive slope, then you're not likely to make that sort of mistake. Now, remember what I said a minute ago. This -2 can be interpreted as the change in the y value when you go 1 unit to the right. So let's look at the diagram and see if that holds true. As we go down 2 units, we go over 1 unit. So by going 1 unit to the right, we have to go down 2 units to sort of stay on this line segment. And this continues, right? Every time we go to the right 1 unit, we're actually having to stay, we're actually having to drop 2 units. If it makes it easier, you can think of going to the right 1 unit and down 2 units this way, to the right 1 unit, down 2 units, to the right 1 unit, and down 2 units. And so this lines up with our interpretation for slope, going down 2 units for every unit you go to the right. The formula, the formal way to write the slope, looks like this: y2 minus y1 over x2 minus x1. And again, as with the distance formula, it doesn't really matter which one's 0.2 and which one's 0.1, as I just demonstrated above, as long as you're consistent. You can't say, well, for the purposes of taking the difference in the y's, I'll make one of these points 0.2 and the other one 0.1, and then switch it when you do the x's. That will definitely lead to some mistakes. Now, one of the really nice things about coordinate geometry is that you can get a visual understanding of the set of solutions to an equation. So let's think about a simple equation like x plus y equals 5. Now, it's easy enough to come up with some solutions to this. One thing to keep in mind is that there is an infinite number of solutions. That's why it's really nice to be able to graph these, because then you can get a visual interpretation for all of these infinite number of solutions. So we can think of a few. For instance, if we make a little t-table, which is extremely useful for graphing, we can pick some values of x and y. So for instance, if x is 0 and y is 5, then 0 plus 5 is equal to 5. So that is a solution to this equation. It's an ordered pair. You need both an x and a y value to represent a solution. We could also make x equal to 1, in which case y would only have to be 4. Or we could make x equal to 2, y would have to be 3. And you can see you can generate some points quite quickly here. If x is 3, y just has to be 2. If x is 4, y can be only 1. And if x is 5, y just has to be 0. Now, I've picked positive integers, but there's no reason why we couldn't have picked some fractions or decimals. And there's also no reason why we couldn't have picked some negative numbers. X could be -1, y would be 6, as an example. So what does this look like when you actually graph it? Well, let's do our axes, and let's plot the 6 points that I actually have in my t-table. So a point 0.05 means I'm going 0 units to the right of the origin and 5 units above the origin. So 1, 2, 3, 4, 5. So that's my point right there, 0, 5. And then 1, 4 means I'm 1 unit over and 4 units up. So that's my point 1, 4. And 2, 3 means I'm 2 over, 3 up. And this one is 3, 2. This one is 4, 1. This one is 5, 0. And, if you want to, you can do more here to convince yourself that this will actually continue on. And we could actually fill in every point in between any two of these. In fact, we could find an infinite number of solutions between any two of these. And the nice thing is that the points all fall on a line, which is why we refer to this equation as a linear equation, because the solutions fall on a line. Now, there's a lot of different ways to write linear equations. So we could take this, I'll move this down a little bit, we could take this equation, x plus y equals 5, and we could solve it for y. In other words, isolate y on one side of the equation, and the way to do that would be to subtract x from both sides. We could write it as 5 minus x, but more commonly it would be written as minus x plus 5. And we refer to this way of writing the equation as a slope-intercept form. Now, why do we refer to it as the slope-intercept form? Well, it turns out that the coefficient on x, which is -1 here, corresponds to the slope of the line, and the plus 5 corresponds to the y-intercept, and we use typically the letter b to represent the y-intercept. So the y-intercept tells you where it crosses the y-axis, and you can see it crosses the y-axis at 5, so we refer to that as the y-intercept. The slope, -1, well, let's just look and see if the slope is -1. Is it dropping a unit every time we move to the right 1 unit? Yes, so this has a slope of -1 and a y-intercept of 5. So that's an example of visualizing all of the solutions to an equation, and again, it gives rise to the name of the equation, linear equation. You can do this same technique with just about any type of equation. As long as you can actually calculate solutions, you can figure out some points and then you can graph those points. The trouble is you're not always going to know how the function behaves, and therefore the shape of the graph is not always going to be entirely evident even when you have a few points down. So let's take a look at an example that's just a little bit more complicated, and this is an example of a quadratic function. So a quadratic function is one that has a variable squared, an x squared in it, and we're going to look at a fairly straightforward quadratic function, y equals x squared plus 2. So once again, if we make our little t-table, the idea here is that we're just going to pick some values of x pretty much at random and figure out what the y values are, and then we'll plot the points and see if a shape emerges. It really isn't that much more complicated. So let's pick -2, -1, 0, 1, and 2 as our x values and see if that gives us anything to work with. Now, of course, I have a little bit of inside knowledge, having worked with this function, and I know that those x values are going to give us something at least to work with. You might not always be so lucky. So we take this value of -2 and we replace the x in the equation with -2. When you square -2, you get 4. Add 2, you get 6. So that's one solution to this equation. Now we can do the same with -1. When you square it, you get +1 plus 2 gives you 3. When you replace the x with 0, you get 0 when you square it, and then you add 2 and you get 2. 1 is going to give you the same value that we got with -1, because when you square a positive or a negative, you're going to get the same thing. So we're going to get 3 and then 6, and so this function exhibits some symmetry. Now let's see what this looks like when we actually plot those points. So they're all positive, so we don't really need to have much below the x-axis here. And we've got 0, 2. I'm going to start right in the middle because that's the lowest point. So that's 0, 2. And then we've got -1, 3 and +1, 3. So when we go to the right one or the left one, we're going up 1 unit. And then we've got -2, 6 and +2, 6. So we've got 1, 2, 3, 4, 5, 6. So it's definitely not a linear function. It's sort of a V shape, and you could try plotting some more points, perhaps values in between the ones we've chosen. So values like 1/2 or -1/2 or 1.5, and then just verify for your own content that these actually follow a curve. And the name of the curve is a parabola. And we refer to this point at the bottom as the vertex of the parabola. And it's not a sharp point, it's a rounded point. You can use some graphing software. I highly recommend using one on the web called Desmos, D-E-S-M-O-S. It's free, it runs in most browsers, and then you can try experimenting with graphing things like this. So the point here is that every one of the points that we've graphed, including the ones that are in between the ones we've graphed, represents solutions to this equation. So 0, 2 is a solution, 1, 3 is a solution, 2, 6 is a solution. All of these points and all of the points that we've implicitly graphed by filling in this curve are actually solutions. And it's really wonderful because instead of just having this abstract equation y equals x squared plus 2, we've now got a visual and a shape attached to it, and we can think of this as an actual object or a shape rather than just some abstract equation.